Hello, everybody. This video, we're going to do two basic rules from probability, what are called the multiplication rule and the addition rule. So what I'm going to do is just define the rules and do a couple of very quick examples in this video. So I'm hoping to keep this one short and very basic, and then we'll do some more examples in some following videos to get a little more detail on these things. So let's start with defining them. Okay, so we've got, just arrange my screen here. All right, so let's take a look at these two rules. So we've got the multiplication rule. This is what we do when we have and events. So in general, I'm going to use A and B are events. Okay. And so the multiplication rule tells us how do we compute the probability if I'm asking about an event A and B. In previous videos, we've really just been computing probabilities by writing out sample spaces and counting, right? And that's a really great way to introduce the idea of probability. However, it is definitely not the way you want to compute probabilities when typically your probabilities are dealing with sample spaces that are huge or not very, if they're not even discrete, you can't really write them down in the same way. So we need to start developing some better techniques, and this is our first one. So the probability of A and B is going to be the probability of A times the probability of B given A. Okay, so if you hopefully know how to compute these, right, and we'll see examples, we'll see why sometimes we might know this, that we can come up with these and then compute this. Just to be clear, the ordering of the letters here doesn't matter. This is equivalent to saying the probability of A and B is equal to the probability of B times the probability of A given B. Okay, notice I just switched the roles of A and B. There's nothing special about the order of A and B in this AND statement. So you can use either of these, right? And sometimes you might have information about one or the other that makes it easier to do, right? We have actually seen this version previously. We defined the probability of A given B as the probability of A and B divided by the probability of B. Well, this is just, if I multiply the probability of B to both sides, this becomes this equation. Okay, so that was our definition of conditional probability. Just use the same idea. Okay. One other thing to notice about this rule, if A and B are independent, then remember that means the probability of A given B is just the same as the probability of A, or I shouldn't say or, also the probability of B given A is the same as the probability of B. Those were two of the rules for independence. If these are true, then looking at these equations, I can rewrite this multiplication rule as the probability of A times the probability of B, which was also something we said about independent events, right? Because all that's happened is, for instance, probability of B given A up here has been replaced with the probability of B because they're the same number, okay? So this version of this formula only works if A and B are independent. Okay? So it's always safe to assume, it's always safest to assume events are dependent. And only use this if you're 100% sure they're independent. Because if you assume they're dependent and you use this version and it turns out they're actually independent, you'll find out, because when you go to compute this number, however it is that you're getting this number, you'll find out it's the same as the probability of B or vice versa, and it'll turn into this equation anyway. So this is the safer form of the equation, but if we know something's independent, we're allowed to use this equation. All right, then our addition rule, we'll do examples of both of these in a moment. Our addition rule is the following. The probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Okay. So again, I'm going to try to show you where these formulas come from a little bit, give you a little intuition on them, but we also just need to know what these rules are. Notice we have a special case for this one. If A and B are mutually exclusive, then the probability of A and B is equal to 0. That's the definition of mutually exclusive. And then the probability of A or B is simply the sum of these two probabilities. Again, this is only if A and B are mutually exclusive. Okay, so there's our two rules, our addition rule and our multiplication rule. I want to point out one other thing about them. Notice that A or B, the probability of A or B is going to tend to get bigger. We're adding two positive numbers together. We'll see this one's generally going to be, well, let's actually start up here. A and B, the probability of A and B is going to tend to be smaller than each of these. Remember, probabilities are almost always less than 1. The biggest they can be is 1, and most of the ones we deal with are going to tend to be smaller than 1. So you're taking the probability of A and multiplying it by a number smaller than 1. You're making it smaller, right? So the probability of A and B is less than the probability of A almost always. Sometimes it could be equal. And the probability of A and B is going to be less than the probability of B, right? So it's going to be less than both of these. This sometimes, I think, messes with our intuition because when we think of and, we think of getting bigger, but it's the opposite. And then down here, it goes the other direction. The probability of A or B tends to be bigger than each of them independently because we're adding together things that are almost always bigger than 0. Probabilities can be 0, but most of the ones we look at are positive, so you're taking two positive numbers and adding them together. We are subtracting something, but as we just said, the thing we're subtracting is usually smaller than either of these. So in the end, the sum of these two things minus something smaller than both of them is bigger than either one independently. So we tend to get bigger probabilities with or statements, smaller probabilities with and statements, which kind of like goes backwards, I think, to how a lot of people think about those words. Okay, let's do some examples of each of these rules that hopefully give us a little more meaning before we get into some harder examples later. Okay, so let's start with a simple experiment. Let's consider an experiment where I'm going to roll a 4-sided die twice. Okay, and I'm going to look at the events. The first roll is less than 3, and B is going to be the event. The second roll is more than 1. Okay, so those are my two events. Let's just write out the sample space and do this how we've done this previously, and then see how it matches up with our, well, I haven't said what probability I want to compute. So let's look at the probability of A and B. So let's do this by looking at the sample space and counting, and then see how it matches up with the multiplication rule. So our sample space, right, I'm going to do it this way. 1, 1 means the first roll is 1, the second roll is 1, 1, 2 is the first roll 1, then 2, and so on. So here are all oops, 4, 1, 4, 2, 4, 3. Here are all the rolls we could have, all the outcomes we could have, right? So if we want to compute A and B, we're looking for all the roles where the first one is less than 3, right? So that means I'm looking on the, let's see, how do I want to mark this exactly? Less than 3 means I'm looking to the left of this line, right? Because I'm looking at the first row less than 3, so that's a 1 or a 2, so that's these 2 columns. And then the second row more than 1 means I'm looking above, or sorry, below this first line, right? That's the second row has to be a 2, a 3, or 4. So I'm looking to the left of this line, below this line, which means it's all of these outcomes here, right? So how many outcomes are here? 1, 2, 3, 4, 5, 6. And our total outcomes, we can count them up, we have 16, okay? 6 out of 16. If we want to, we can reduce this to 3/8. But let's look at this a little more geometrically for a second. Let's pretend I hadn't just counted these and I wanted to know how many outcomes were here. Right. Well, what I notice is this is I can think of this like almost like a square or a rectangle. There are 2 columns that each has 3. So this is going to have 2 times 3 entries in it, right? If I have 2 columns, each with 3 entries, 2 columns full of 3 entries. And the size of the whole rectangle or square is 4 columns by 4 entries. Okay. Now, normally we would just multiply across and we would see we have 6 over 16 just we got up there. But I'm going to use a little algebra and write this differently. This is the same as writing 2 out of 4 times 3 out of 4. Okay. What is 2 out of 4? Well, this 2 came from how many columns I had here, which was also how many of my first rows were less than 2. In other words, out of the 4 possible rows I could have made a 1, a 2, a 3, or 4 with the first row, there's 4 possibilities, 2 of them were less than 3. In other words, this number here is the probability of A. Right? This here is the 3 rolls greater than 1, rolling a 2, a 3, or a 4, represented by these 3 rows, in my second roll out of a possible 4 options, right? I could have rolled a 1 through 4. I'm counting the options 2 through 4. In other words, this 3 out of 4 was just the probability of B, right? And we might recognize this now as our multiplication rule in the case that we have independent events. These rolls are independent. The second roll doesn't keep track of what I got on the first roll and try to make up for it or something like that, okay? So we're seeing the multiplication rule emerge from this little diagram, okay? That's as much as I'm going to give us in terms of intuition on this, but that I hope helps to some extent, okay? We'll do some more examples later in other videos, maybe that might help as well, but I want to just keep this one simple for now. And this is a little example of our addition rule. So let's move now to, our multiplication rule. Let's move to our addition rule. And let's consider the same experiment. All right. But I'm going to name some new events. So I think I'll write out, I'm just going to write it out again so we have a clean sheet. The experiment is roll a 4-sided die twice. Let's call something like, I don't know, I'll just use M is equal to roll a 3 first, N is equal to roll a 4 second. Okay, and we want to compute the probability of M or N. Okay, so I'm just going to quickly write out the sample space again. Oops, I made the same mistake last time. Don't like that 4 for some reason. Okay, so there's our sample space. Let's look at the probability of M or N, right? So let's just go through each right? What we're asking for is how many outcomes are in M or N, in either one of them, divided by how many total outcomes there are. Well, we already know there's 16 total outcomes. Okay, but let's look at, let's count up these. So rolling a 3 first is this whole column, right? All of these have 3 first. Rolling a 4 second is this whole row, right? So let's count how many we have, but let's kind of do a shorthand. I've got 4 in this column, so let's just take those 4. I've got 4 in this row, so I've got 4 more, but we notice we've overcounted. We counted this outcome twice because it's in both of them, right? So I should subtract 1, which gives me 4 plus 4 is 8, minus 1 is 7. We get 7 out of 16, right? This might not have been faster than just counting, but I want to illustrate something in a second, okay? So again, we counted 4 here, but realized we counted that one twice. Let's do some algebra on this expression here, right? With fractions, I can do 4 out of 16 plus 4 out of 16 minus 1 out of 16, right? That's just rules of fractions. Okay. But let's notice what these numbers are. 4 out of 16, where did this come from? It was the 4 in the row from rolling a 3 out of the total. This was the probability of M. This 4 out of 16 came from the 4 in this row from rolling a 4 second. The subtraction was the one overcounting. That was the one that appeared in both rows. In other words, this was the probability of M and N. And this is exactly the addition rule, right? We add the probabilities of each one by themselves, but we have to subtract the places where they overlap because we overcounted it. We counted it twice, so we subtract it once, leaving us with only 1 counting, right? We only want to count everything 1 time, okay? So that's kind of a visualization of where this addition rule comes from. Let's do one more quick example with it on this same experiment. Let's now add the events E equals roll a sum greater than 6, and F is roll a sum less than 4, right? By sum, I just mean we roll twice, we add the 2 numbers together, okay? And let's do the probability of E or F in this case. All right, let's go back to our picture. If I roll a sum greater than 6, it means my sum has to be 7, 8, and on up, right? Well, if I look at this and I can just do these additions in my head, I see that I can divide it this way. This little bottom triangle. These 3 outcomes here, these 2 have an addition, a sum of 7. This one is 8. Everything else has 6 or 5 or 6, 5, 4, or 3, or 2, right? So that's 3 out of, there's 3 there. Let's add in, let's count all of the rolls that are less than 4. That's this upper triangle here, right? A roll of, this sums to 2, this sums to 3, this sums to 3, the rest sum to 4. 4 is not less than 4. So there's another 3 up there. And notice there's nothing we have to subtract because we didn't count anything twice. These 2 events don't overlap with each other, right? And so this, of course, is 6 out of 16. But again, let's take a look at it this way and see this is just the probability of E plus the probability of F, right? And there's our addition rule again, okay? In this case, we didn't have to subtract anything because the probability of E and F is equal to 0. That was our special case of this rule where they're mutually exclusive, right? So we see it here, those 2 events don't overlap with each other. You can't roll something that has some larger than 6 and at the same time be less than 4. Okay? All right, that's it for our introduction to these rules. I'll do some more videos a little later with several more examples so we can dig a little deeper into these ideas. All right, thanks everybody. See you next time.